This is the helium-4 GUMII model, and it is where we left off in part 1. We learned that this is the charged particle that makes up the alpha rays that Rutherford identified back in 1899. All known isotopes of helium have been shown in the chart on the right, where stable and radioactive isotopes are indicated with different color codes. Recall that we used the website listed and the GUMII graphic construction rules at the bottom to create this isotope chart. If these construction rules are not familiar, go back and review part 1. Next, let's add a fifth triangle or neutron and form helium-5. From the helium isotope chart, we know that this GUMII model should contain 5 triangles and 8 electrons. In order to add a new triangle edge at right angles to an old triangle edge, one of the neutron electrons must fill up the go-to zone of the previous helium-4 nucleus. So this is a nucleus that doesn't have a stable go-to zone, and normally it would undergo beta decay, but it doesn't. And the obvious question is, why not? Well, note that the fifth triangle kind of hangs on as an appendage with only 4 up quarks involved in any binding. If a quark electron were to eject, then the fifth triangle would look like a proton trying to bind onto 4 other triangles that have a +2 net charge. This is apparently too much repulsion, and the fifth triangle goes with the quark electron, making the overall result look like a neutron decaying out of the nucleus. So this nucleus decays back to helium-4 instead of undergoing beta decay to lithium-5. And although the GUMII model illustrates this susceptibility to bypassing beta decay, the model certainly didn't predict it. The decay sequence was taken from the website database shown at the bottom of the slide. This is the same website that lists all known isotopes used for the GUMII isotope charts. Next, let's add a sixth triangle or neutron and create helium-6. Of course, we're now trying to add a neutron to a nucleus that sheds neutrons. How can helium-5 take on another neutron when it can't even hold on to the added neutron from the previous slide? Well, logically it can't. What we're really doing is adding 2 neutrons to helium-4. From the helium isotope chart, we know that this GUMII model should contain 6 triangles and 10 electrons. The sixth triangle could be added to several edges, but it will always be drawn first at a location where new virtual quark triads can be formed, because of the more powerful additional strong and weak force binding. Note the location where 2 new virtual quark triads are created. This increases the strong and weak force binding so that now the neutron appendages are prevented from flying off. But the lack of go-to zones sets this nucleus up for beta decay. In this case, unstable helium-6 will change to stable lithium-6 because a go-to zone will be opened up. And as we go to the next slide, notice the quark electron with the yellow highlight circle around it. In this slide, a moment of time has passed and the helium-6 nucleus has decayed into a stable lithium-6 nucleus. We still have 6 triangles, but the quark electron within the yellow circle is gone, and there is now a stabilizing go-to zone in its place. After constructing a lithium isotope chart, we see that this nucleus should have 6 triangles and 9 electrons. And we also note that only lithium-6 and lithium-7 are stable among the 9 known lithium isotopes. Lithium is a soft silver metal. It is the first nucleus we've analyzed that is not a gas at room temperature. But before we create lithium-7, let's look at how some of the data for lithium-6 on the isotope chart was originally collected. This is a cloud chamber photograph. In it, we can see the evidence of the beta decay shown in the previous GUMII model with our own eyes. C.T.R. Wilson invented the cloud chamber in 1911. Wilson built a chamber that was supersaturated with water vapor. As he had envisioned, excess moisture formed in drops on the tracks of ions created by the passage of ionizing radiation. And in the cloud chamber photograph, electrons can be identified by a curved track in the presence of a magnetic field. The much heavier residual lithium-6 atom is neutral and goes in a straight path for a much shorter distance. Scientists soon noticed that a lot of mass was missing after beta decay occurred. A lot leaves as kinetic energy when particles fly apart, but that still doesn't account for all the missing mass or energy. In order to account for all the change in mass or energy, an additional particle had to be released during beta decay, and it was called the antineutrino. The neutrino was theorized as a particle that carries away missing energy and helps save several nuclear conservation laws from being violated. Like gluons, the neutrino is too difficult to detect directly, but indirect measurements have confirmed the existence of neutrino events. The GUMII models show nuclear structure geometrically with understandable 3D graphics. GUMII models do not predict, but rather generalize, by counting quarks, why neutrons are stable in some atoms and unstable in others. GUMII stands for Generalized, Understandable Models of Intranuclear Instruction. So why do the quarks and electrons of a proton form a kind of three-sided pyramid? Why don't they just all reside on the checkerboard floor in the same 2D plane? Well, if they did, the 3D world as we know it probably wouldn't be here. Clearly, something happens to the electron before it's pulled into the plane of the quarks. What happens is that at 500 times the diameter of a quark, the electron is changed such that it starts swapping a neutral particle called a gluon with the other quarks, and this binds them together at a fixed distance into a proton. It does this by changing the electron into a neutral particle called a gluon plus a new quark electron, and then exchanging the gluon with other quarks. The electron has a symmetrical go-to zone where it can reform or hop to during this exchange. An important thing to notice is that in the proton, the electron can be distorted into a ripple and reform over and over again. It will hop or reform back and forth past the three quarks like an endless oscillator that doesn't lose energy. The specific variety of the electrical force that binds quarks together is called the strong force, and it always involves a gluon exchange among quarks. It is not called the Roche limit for gluons, but it's kind of like that. We can't see any of this happening directly in the nucleus, and we can't isolate any of the quarks or gluons outside the nucleus. But we can generalize that this is happening because, as we shall learn next, a very similar thing happens to electrons outside the nucleus, and those we can see. After three quarks bind up the first available electron, there is still a net +1 charge remaining to bind up a second electron. So why don't all protons bind up the next available electron and just naturally turn into neutrons? What happens is that way beyond gluon swapping range, the next available electron is changed such that it starts swapping a neutral particle called a photon with the nucleus as it tries to become the proton's second electron. When the photon gets to the nucleus, there is no allowable location for it to reform into an electron, so the photon must leave the nucleus and return to orbit. This binds the second electron to the proton at a relatively large fixed distance and forms an atom of hydrogen. When we study the neutron next, we'll see that an electron can't form in the one available go-to zone, or the nucleus becomes unstable and undergoes radioactive decay. And from now on, when we talk about atoms, we'll often refer to an electron that resides outside the nucleus as an orbital electron. This is just a reminder that the location for this electron is in an orbital shell of the atom, not in the nucleus. So what is meant by the phrase way beyond gluon swapping range? And if three quarks can exchange photons beyond gluon range, why don't they do that with the first electron? Well, maybe they do, but the first electron would now have an allowable location to reform and would just stay with the quarks. So if that happened, all the particles would be drawn closer until they reached a kind of Roche limit for gluon exchange, and then a proton would be formed by the strong force. Anyway, the phrase way beyond gluon swapping range means that at about 10,000 times the diameter of the proton can distort or change a second electron into a different kind of ripple or standing wave. It does this by separating the second electron into a neutral particle of light called a photon, and also into a new electron, and then exchanging that photon between the nucleus and the new orbital electron. It sounds like magic, but in the world of quantum mechanics, an electron can always be turned into a photon and another electron. We see this when an electron gives off a photon of light as it hops and reforms closer to the nucleus in a lower orbital shell. This is also why orbital electrons seem to randomly reform and hop around the nucleus in electron clouds. We shall see in Part 2 why electrons can't possibly rotate around an atom in circular orbits. An important pattern to notice is that gluons are the neutral exchange particles for quarks, while photons are the neutral exchange particles for electrons. And because we can see the photons of light emerging from orbital electrons, we can generalize that gluons are emerging from quark electrons in a similar manner. The specific variety of the electrical force that binds an orbital electron to the atomic nucleus is the electromagnetic force, or EM force. The EM force always involves a photon exchange between two electrons or even potential electron locations. It is not called the Roche limit for photons, but it's kind of like that. Let's observe something very interesting about the angle at which quark electrons repel. If you hold two negatively charged balloons together in outer space and then let them go, you would expect the balloons to repel straight away from each other in a straight line, otherwise known as an angle of 180 degrees. But the electrons in neutron beta decay don't do that. For comparison, what angle do billiards glance off at when they have the same size and weight? The answer for billiards is always 90 degrees. And in the special photo on the right, we can see the actual tracks of a neutron ejecting an electron, and surprisingly, it's at 90 degrees. And while the lightweight electron is being smacked away at 90 degrees, the much heavier nucleus is only slightly budged. So the ejected electron behaves much more like a billiard ball being smacked away than like a balloon being released. And this result agrees well with the 3D GUMII oscillator models for the proton and the neutron. Smashing atomic particles into other particles usually forces interesting events to occur. And normally, these interesting events only occur at specific energy levels. For example, the alpha particles that we'll soon talk about are always knocked loose at specific energies. But for beta decay, electrons can be knocked out of neutrons at a lot of different energies. For a long time, scientists couldn't explain why there was this wide range of binding energy for an ejected electron. It turned out that the antineutrino was the particle carrying away the variable amounts of energy. The GUMII models generalize graphically why this energy variation occurs. It's just the two quark electrons being sometimes more and sometimes less in sync. When they get out of sync, beta decay will occur spontaneously. But should an accelerated particle strike when the two quark electrons are nearly out of sync anyway, then it will appear that very little energy was required to overcome the binding force holding on to the second electron. Or should a collision occur when the two quark electrons are well synchronized, then the binding force would appear to be quite high. The specific type of electrical force that provides the binding energy for the ejected electron from the neutron is called the weak force. The weak force does not involve a gluon exchange with the three quarks. It is primarily the residual attraction between one of the quarks and the departing electron or antineutrino, a simple quark to electron binding, or a Q to E binding in shorthand. For completeness, we note that physicists have identified the boson as the exchange particle during weak force interactions or bindings. The time that it takes for the two quark electrons to get out of sync and repel from each other varies from neutron to neutron. But if we had 8,000 neutrons, we know that on average half of the neutrons would decay in 12.8 minutes. This is called the radioactive decay half-life. So at the end of 12.8 minutes, only 4,000 of the 8,000 neutrons will be left. At the end of 25.6 minutes, only 2,000 undecayed neutrons will be left. At the end of 38.4 minutes, only 1,000 neutrons will be left, and so on until all the neutrons have taken part in beta decay. Next, let's add a seventh triangle, or neutron, and form lithium-7. From the lithium isotope chart, we know that this GUMII model should contain 7 triangles and 11 electrons. Normally, that would leave 2 go-to zones and make the nucleus unstable. But apparently the concentration of 3 electrons at the top of the model effectively shields one location from use by the other electrons. It's like surrounding one of the chairs in a game of musical chairs so that no one can use it. The result is that there is only one usable go-to zone instead of 2 go-to zones, and this becomes a stable atom. Next, let's skip lithium-8 and make a smooth transition to beryllium-8. We'll do this by adding an 8th triangle that's a proton instead of a neutron. This allows us to skip some extra shuffling of graphics that is shown separately in a lithium-8 slide set for those who are interested. We'll construct a beryllium isotope chart on the next slide, and that will show that this nucleus has 8 triangles and 12 electrons. But by now, we should be able to calculate these numbers in our head, just given the fact that beryllium-8 has 4 protons and 4 neutrons. Beryllium-8 is another unusual lab isotope that doesn't undergo straightforward beta decay. It is a light atom that actually undergoes alpha decay. Recall that spontaneous natural alpha decay only occurs in atoms with more than 143 triangles. The reason alpha decay occurs is that 2 new virtual quark triads are created, giving us locations for 14 electrons. But there are only 12 electrons available, and that leaves 2 go-to zones. And since a stable nucleus only wants to trade energy with one go-to zone, some kind of ejection has to occur. What happens is that the 2 go-to zones can be shared nicely by 2 helium-4 nuclei. So the beryllium-8 nucleus splits in half via alpha decay. In this slide, the beryllium-8 nucleus is shown next to a chart of the 10 known isotopes of beryllium. We see that only beryllium-9 is known to be stable. So next, let's add a 9th triangle or neutron and form beryllium-9. 2 new virtual quark triads are formed, and normally that would provide 2 additional electron locations. However, the virtual quark triad of an adjoining neighbor already fills one of those locations. So compared to beryllium-8, beryllium-9 picks up 1 go-to zone and is stable. Next, let's mentally add a 10th triangle or neutron and form beryllium-10. This fills out the lower edge triangle attachments. But because it's in back and doesn't show up well graphically, it's not shown. As was the case for the prior lower edge triangles we added, 2 new virtual quark triads are formed. But no additional electron locations are gained because neighboring virtual quark triads already fill them both. So the beryllium-10 nucleus ends up with no free go-to zones, and is thus a candidate for beta decay into a stable boron-10 nucleus. Note that the last lower edge attachment point is filled by the 10th triangle. So where should one attach the 11th triangle or neutron? Normally, the GUMII models add a new triangle edge at right angles to an old one. That's how the new triangle can line up 2 of its quarks with existing electron locations in the nucleus and maximize weak force binding, first illustrated in Part 1. But when building on the boron-10 nucleus, the 11th triangle has the opportunity to align 3 of its quarks with existing electron locations in the nucleus instead of just 2. This is accomplished by adding the 11th triangle at the top as shown. Note there is 1 stabilizing go-to zone at the bottom of the boron-11 model, because evidently 2 electrons aren't enough to force out a go-to zone when all the virtual quark triads have been filled. So this is a stable nucleus. By the time the 12th triangle is added on the bottom for carbon, all the tightly coupled structures are used up. The 3 quark electrons on top will attract triad 11, and a similar set of quark electrons on the bottom will attract triad 12. One way to interpret this is that structure dominates radioactive decay for the light nuclei, while nuclear shell or wave equation models dominate radioactive decay for the heavier nuclei. There are some papers from Europe plus some basic generalized evidence that suggest this is what happens. The generalized evidence has to do with atomic bonding angle, something that quantum mechanics doesn't predict very well. If we look at molecules of water and hydrogen sulfide, both have 2 hydrogen atoms bonded to a larger third atom. The standard model wave equation solution for the atomic bonding angles of water and hydrogen sulfide should both be 90 degrees. But the GUMII models have clusters of quark triads located at 120 degrees of symmetry, and that should reinforce a bonding angle of 120 degrees. But the measured bonding angle for a water molecule is 105 degrees. This appears to be a compromise or balance between the 2 angles when dealing with an oxygen-16 atom. But for sulfur-32, an atom that has 32 triangles, and the same 2 hydrogen atoms attached, the atomic bonding angle is down to 93 degrees. The triangles are just too loosely bound, and the GUMII structure seems to have lost almost all influence by the time the mass numbers get much above 16. We must now ask, what forces cause radioactivity? Because in physics, everything is caused by a force. Physics defines a fundamental force or interaction as one that is permanent and changes strength with distance. Gravity is one such permanent fundamental force. It exists everywhere matter is present, and it doesn't use up any energy to provide a force of attraction between particles of matter. Gravity will still be here long after we're all gone. And gravity weakens at greater distances. A spacecraft near Mars will not notice Earth's gravitational pull. Yet inside a star, hydrogen atoms and protons will get pulled together with so much force that fusion into helium occurs. The fusion process releases gamma radiation, and we'll get around to discussing gamma rays in Part 2. So gravity is a fundamental force that causes radioactivity in stars. Gravity also causes planetary tidal force, and that, in turn, can swell the oceans and stretch matter apart. At black holes, the tidal force becomes strong enough to rip atoms apart and cause radiation. Even if you've seen the tides on Earth that are caused by lunar gravity, you've only seen a weak example of what tidal force can do. Go out on a clear night with binoculars and look at the rings of Saturn. You will be looking at matter, not liquid, but matter that has been stretched apart by tidal force. Are the rings of Saturn radioactive? After all, they have been stretched apart by the tidal force of gravity. The answer is no. The tidal force around planets is much weaker than at a black hole. Too weak to rip atoms apart, but strong enough to stretch dirt and ice particles apart. So how can the same attracting force that compresses hydrogen in stars also cause the ring stretching around Saturn? The secret is that the rings are all within Saturn's Roche limit, where huge planetary tidal stretching force wins out over the tiny particle-to-particle gravity. Scientists know that the rings of Saturn consist mostly of particles of frozen water and other ices. One possible source for the ice particles is believed to be comets, because comets are basically dirty snowballs flying through space. When a comet gets too close to Saturn, tidal force can stretch the loose mixture of matter into the tiny ice particles that make up the rings. The way tidal force works is shown on the slide. When a comet is far enough away from Saturn, it experiences no gravitational pull. But as it gets closer, the front side may experience 100 pounds of pull, while the back side experiences 90 pounds of pull. This is a stretching force of 10 pounds, and 10 pounds is probably enough to rip apart a snowball. Scientists have calculated the amount of planetary tidal force that is required to rip snowballs and other types of intermixed matter apart. Each planet has a point of closest approach at about 1.3 times its diameter, where this level of stretching force is achieved. This point of closest approach is called the Roche limit. You can do a quick estimate of the Roche limit by taking the outline of a planet and placing it alongside as shown on the slide. Note that the rings of Saturn are all shown to be within one diameter of the planet's surface. At black holes, there could be enough tidal force to disrupt the atom and cause radiation. But are there black holes near Earth? Well, if there were, our bodies would be incredibly stretched by tidal force, stretched into long, thin strings. So no black holes are anywhere near our part of the universe. But don't think you're safe from tidal force yet. Because the truth is that tidal force doesn't have to be caused by gravity. Any attracting or repelling force that weakens with distance will tend to stretch matter that gets too close. And surprisingly, there is a stretching force right here on Earth that is a billion times stronger than gravity. So why aren't we all stretched into long, thin strings? The electrical force is the hidden stretching force that is much stronger than gravity, a 1 followed by 40 zeros times stronger. The electrical force is strong enough to cause radioactivity. It is a fundamental force because it's permanent and changes with distance. The electrical force is what sticks a balloon to the wall after you rub it in your hair. If balloons and walls lasted forever, the balloon would stick forever. If you look at the two-person example on the slide, you can see how powerful this force really is. Two 100-pound people with 1 pound more electrons than protons in their bodies and at arm's length would have enough repelling force to lift the Earth. Since people don't repel each other off the planet Earth, and since our bodies aren't stretched into long, thin strings, we know that electrons and protons must be intermixed around us with perfect balance. So this new type of tidal force, known as the electrical force, is all around us. We just don't feel it because of perfect balance. But how is this perfect balance achieved? Well, it's all done with atoms. So as we come to the end of Part 1, let's review what we've learned so far. Rutherford identified 3 kinds of radioactive rays: alpha, beta, and gamma. In Part 1, we have learned that alpha and beta rays are really charged particles ejected from the nucleus. In Part 2, we'll learn that gamma rays are not charged particles, but rather neutral photons. In Part 1, we learned about 4 forces: gravity, electrical strong force, electrical weak force, and electrical EM force. Note that the weak force and EM force have recently been combined into the electroweak force under the Standard Model. In Part 1, we learned that except for gravity, all of these forces are variations of the electrical force, and they are all well described by the Standard Model. In Part 2, we'll learn that there is something called string theory that combines even gravitational force. So what causes radioactivity, or in particular alpha and beta rays? What force determines when the nucleus will disintegrate? Well, on Earth it's not gravity, and it's not the strong force. Primarily it's the weak force that determines the absence of any shared go-to zones, and that's what governs the types of radioactivity that we've studied so far in light nuclei. And finally, in the credits section for Part 1, we see once again that GUMII stands for Generalized Understandable Models of Intranuclear Instruction. The 3D computer models of the nucleus were made with Magic Camera ray trace software. Most of the knowledge and all of the references were garnered from the 3 authors listed.